Hello everyone, welcome back to Code Lane. In today's data structures and algorithms video, we are going to learn about space complexity. When learning an algorithm, most people focus on how fast the program runs. However, speed is not the only thing that matters. Memory usage is also very important. Imagine that an algorithm runs very fast but uses a huge amount of memory. In real-world applications, that can become a serious problem. Therefore, software developers must consider both speed and memory efficiency. Space complexity helps us measure how much memory an algorithm requires while it is running. In this video, we will understand what space complexity is, why it matters, different types of memory, big O notation for memory usage, recursion space complexity, and how to analyze space complexity step by step. Let's start with the basic definition. Space complexity refers to the total amount of memory required by an algorithm during its execution. In simple words, it tells us how much memory a program needs as the input size increases. Let's take a real-life example. Imagine you are packing for a trip. If you are going on a one-day trip, a small bag is enough. If you are going on a week-long trip, you need a larger bag. If the trip becomes even longer, you may need the multiple bags. Similarly, when the amount of data increases in a program, more memory may be required. Space complexity helps us understand this memory growth. We often express space complexity using big O notation because it shows how memory requirements change as the input size becomes larger. The formula shown on the slide states that total space complexity consists of fixed space and variable space. Fixed space remains constant while variable space changes depending on the input. Now let's see what is time complexity and space complexity. Time complexity measures how long an algorithm takes to execute. In other words, it focuses on speed. Space complexity measures how much memory an algorithm consumes. It focuses on storage requirements. For an example, if we have an algorithm that processes 1000 records, we may want it to finish quickly. That relates to time complexity. However, we also want to know how much RAM it uses while processing those records. That relates to space complexity. Sometimes there is a trade-off between the two. An algorithm may become faster by using additional memory. Another algorithm may save memory but take more time to execute. Therefore, software engineers often balance both factors when designing efficient systems. Now let's understand why space complexity is important. Memory resources are limited. Every device, whether it is a smartphone, laptop or a server, has a limited amount of memory available. If an application consumes too much memory, several problems can occur. The system may become slow. The application may crash unexpectedly. The operating system may terminate the application. Users may experience poor performance. Space complexity becomes especially important in large-scale applications such as social media platforms, artificial intelligence systems, gaming applications, and mobile apps. For an example, a social media platform may process millions of users at the same time. Efficient memory usage helps the system handle large amounts of data without performance issues. This is why memory optimization is a major concern in software development. Now let's see types of memories used in programs. When a program runs, it uses different types of memory. The four major types shown here are code space, static space, stack space, and heap space. Each type serves a specific purpose. Code space stores the instructions that make up the program. Static space stores fixed variables that remain available throughout execution. Stack space manages function calls and local variables. Heap space handles dynamic memory allocation. Understanding these memory areas help us understand where memory is being consumed inside a program. In the next few slides, we will discuss each type separately. Now let's see about code space. Code space refers to the memory occupied by the actual instructions of a program. When we write source code and compile it, those instructions are stored in memory so the processor can execute them. Code space is usually fixed because the instructions do not change while the program is running. The size of code space depends mainly on how large the program is. Every application, whether small or large, requires some amount of code space in memory. Now let's see what static space is. Static space is memory allocated before program execution begins. Variables that remain throughout the entire lifetime of the program are often stored here. One important characteristic of static space is that its size remains fixed. The memory is allocated once and stays available until the program terminates. Because the size does not change with input, static space often contributes only a constant amount of memory. Now let's see the stack space. Stack space is one of the most important memory areas in programming. It stores local variables, function calls, and recursive calls. Whenever a function is called, the system creates a new stack frame. When the function finishes execution, that stack frame is removed. The stack follows the last in, first out principle, also known as LIFO. A simple way to imagine a stack is a pile of plates. The last plate placed on top of the first plate removed. Stack memory is automatically managed by the system, making it fast and efficient. However, stack memory is limited, which is why excessive recursion can sometimes cause stack overflow errors. Now let's see about heap space. Heap space is used for dynamic memory allocation. Unlike stack memory, heap memory is allocated while the program is running. Objects, linked lists, trees, graphs, and many dynamic data structures use heap memory. Heap memory provides flexibility because memory can be requested whenever needed. However, managing heap memory can be more complex than stack memory. If memory is not managed properly, issues such as memory leaks may occur. Many modern applications rely heavily on heap memory because data sizes often change during execution. Now let's talk about input space and auxiliary space. Space complexity is often divided into two parts, input space and auxiliary space. Input space refers to memory required to store the input data itself. For an example, if we store an array containing 1000 elements, the memory occupied by that array belongs to input space. Auxiliary space refers to additional memory used by the algorithm. Examples include temporary variables, counters, extra arrays, or recursive call stacks. When analyzing algorithms, we often focus on auxiliary space because it tells us how much extra memory the algorithm requires beyond the input data. Now let's see the big O notation for space complexity. Just as we use big O notation for time complexity, we also use it for space complexity. Big O notation helps us describe how memory usage grows as the input size increases. The most common space complexities are big O1, big O(n), and big O(n squared). These notations allow developers to compare algorithms and choose the most memory efficient solution for a particular problem. Big O1 means constant space. This means memory usage remains the same regardless of input size. Whether the input contains 10 elements, 100 elements, or 1 million elements, the algorithm uses approximately the same amount of additional memory. Constant space is considered highly efficient because memory consumption does not grow as the problem size increases. Big O(n) means linear space complexity. In this case, memory usage grows directly with the input size. If the input doubles, memory requirements approximately double as well. Arrays, lists, and many data structures commonly exhibit big O(n) space complexity because each additional element requires extra memory. Big O(n squared means quadratic space complexity. Here, memory usage increases much faster than the input size. A common example is a two-dimensional matrix with n rows and n columns. If n becomes larger, memory requirements grow rapidly. Algorithms with big O(n squared space complexity can become impractical for very large data sets because they consume substantial amounts of memory. Let's look at some common data structures. Arrays store multiple elements resulting in big O(n space complexity. Linked lists also require big O(n space because each node occupies memory. Stacks and queues grow as elements are added, leading to big O(n space complexity. Binary trees store nodes, which also results in big O(n space complexity. Graphs are slightly different because memory depends on both vertices and edges. Understanding these values help us select appropriate data structures for different applications. Now let's discuss recursion. Recursion occurs when a function calls itself. Consider the factorial example shown on the slide. The first call is factorial of 3. Then factorial of 3 calls factorial of 2. Then factorial of 2 calls factorial of 1. Before producing the final answer, all these function calls must remain stored in memory. The storage area is called the call stack. Every recursive call creates a new stack frame. As the number of recursive calls increases, more stack memory is consumed. If there are n recursive calls, then n stack frames may exist in memory. Therefore, recursive algorithms often have big O(n space complexity. This is one reason why recursion can use more memory than iterative approaches. Let's see how to analyze space complexity. When analyzing space complexity, we can follow 5 simple steps. First, identify the input size. Second, count the variables used. Third, check whether arrays, lists, or other data structures are created. Fourth, examine recursion depth and stack usage. Finally, determine the overall big O notation. Following these steps makes space complexity analysis much easier and more systematic. Now let's analyze this example. The algorithm calculates the sum of all elements in an array. The array itself contains n elements, so the input space is big O(n). Apart from the input array, only one variable called sum is used. Since this variable occupies a constant amount of memory, auxiliary space is big O1. Therefore, input space is big O(n), auxiliary space is big O1, and the overall space complexity is big O(n). This example demonstrates how we analyze memory requirements in practice. Before finishing, let's review the key points. Space complexity measures memory usage. Big O notation describes memory growth. Big O1 represents constant memory usage. Big O(n) represents linear memory growth. Big O(n squared) represents quadratic memory growth. Recursion uses stacked memory. Efficient memory management improves software performance and scalability. These are the fundamental concepts you should remember from today's lesson. Thank you for watching this video on space complexity. I hope this explanation helped you understand how algorithms use memory. If you find this video helpful, please like, share and subscribe.